Hey everybody, the purpose of this video is to get a little bit deeper into the math that's going on in that Excel spreadsheet in case you want more math. If you don't want to see the math underlying it, or if you're just happy with the math in the spreadsheet, that's totally fine and the spreadsheet's there. You probably already figured out that you can continue the spreadsheet. For example, it only goes out to year 20. You could easily make it go to year 21, 22, as far as you wanted to, by simply dragging. But I want to some of you might be algebraic. You want to see a formula to kind of see what's going on with that without having to drag it down. For example, you might want to know, well, how much is going to be there after 20 years if Papa put 500 bucks in now and puts 500 bucks in each year, like without having to go through years 1, 2, 3, 4, 5. So I want to kind of walk through that here. So here I started it off. I call it year 0. That's when Max is born. So before the account actually gains any interest, it's worth 500 bucks. That was redundant. Apologies. So after year 1, now we know the value that's in the spreadsheet, which is the actual monetary value of the account. I don't want to focus on that decimal version. I want to focus on the math that's being done to get that. So what's happening is you're taking 106% of the 500 bucks from the previous year, and then Pop is additionally adding 500 bucks on. So there's two 500s up there. I want to make sure you know what each of them are for. This 500 is the 500 that comes down from the previous year. So whatever's here gets brought down here, and we take 106% of it. And then this little 500 at the end here is what Pop puts on at the end. Okay? So that's after year 1. I'm going to leave it just like that. I'm not going to convert that to its decimal because A, it's just going to hide what's going on, and B, you got it in your spreadsheet. Okay. So what happens at year 2? Now remember what happened at year 1. Whatever was up here got dragged down to here. Well, the same thing's going to happen, except we have to drag all of this down to here. So we've got to take this, which is this, and then we have to take 106% of that, and then Pop adds 500 bucks on. Okay? Now this is going to look ridiculous. Probably. I'm guessing anyway. It's going to look ridiculous. But focus it like Excel does in your mind. All I had Excel do was look back one cell, take whatever is in that cell, multiply it by 1.06, and then add 500. That's all Excel is doing. All I'm doing is I'm showing you the math behind what Excel is doing, which is what we're breaking down now. Let's go one more for starters, and then we'll take a step back and kind of look at the big picture, because this is going to start looking ridiculous, because in year 3, we've got to copy all of this down. Okay, that's the previous line. We then have to take 106% of it, and then Pop adds on 500 bucks. So what's kind of cool about this is you can actually see all the deposits he's made so far. There's the deposit he made when Max was born. Here's the deposit after year 1. Here's the deposit after year 2. And there's the deposit after year 3. And you can also see nested all the interest rates that have been applied to them. I want to take a breather for a second. I want you to look at mathematically what is actually going on. For example, that 500 bucks over there is a brand new 500 bucks. It's been put in one time, has had no interest applied to it yet. This 500 bucks right here, that's the 500 bucks from the previous year. That means it's had 106% applied one time to it. This 500 bucks right here, it definitely had this year's interest applied to it, but it also had the previous year's interest applied to it. So this 106 right here, 1.06, and that 1.06 have both been applied to that 500 bucks. And this 500 bucks right here has had 106% of it taken 3 times. So really, another way of looking at what just happened right here, I'm going to write this a different way. In a different way. This can be written as 1.06 cubed times that 500 bucks plus 1.06 squared times that 500 bucks plus 1.06 to the first power times that 500 bucks plus just 500 bucks. That last 500 bucks hasn't had any of this applied to it yet. So it's just the 500 bucks. Now, if you're a fan of exponents, which you may or might not be, you could write this as 1.06 to the 0 power times 500 bucks, because anything to the 0 power is 1. But I'm going to leave it like that. History has told me that that rule tends to upset people more than make them happy. Let's go right above this one in a different way. Can we apply what we just did here to what we did up there? I think we can. Because that 500 bucks has had nothing applied to it. This 500 bucks has had 1.06 applied to it. Excuse me, this 500 bucks, yes, has had this 1.06 applied to it. And this 500 bucks has had both of these 1.06s applied to it. So you see what's going on. I'm going to write the same way as I did down here, so as to be consistent. You see what's going on? Each additional year, the earliest amount increases by 1. But each successive amount also increases by 1. But they are a year, 2 years, 3 years behind. So every time you add another year, for example, year 4, we're going to skip right ahead down to the next line. This one was 1.06 cubed times 500 bucks. It is now going to be 1.06 to the 4th times 500 bucks. This one will be 1.06 cubed times 500 bucks. This one will be squared. This one hanging out on the end here will be to the 1st power. And then don't forget, Pop has to put the 500 bucks in. Plus 500. Make sure you can see that on the camera. I think I might be getting off the screen. Oh, you can see it there. It's kind of small. So really, if you think about it, to figure out for any line what the total value is going to be, you start with the year and do 1.06 times that year that many times. So it's 1.06 times 1.06 times 1.06 to whatever power that year is. So this is 4 years, it's 1.06 to the 4th. If it were 20 years, it'd be 1.06 to the 20th. And then you simply have one term down until you get to Pop's most recent deposit of 500 bucks. Now I'm hoping that you're seeing the problem with this. There is a potential problem if you have interest in saving your time and being wise with your time. Suppose we had to do it for 20 years. Then you're going to have 1.06 to the 20th times 500, plus 1.06 to the 19th times 500, times 1.06 to the 18th, and so forth and so on. And you don't want to do that, do you? No, of course you don't want to do that. What you want to do is you want to have a formula that you can simply plug the number 20 into, which will kick out how much money is going to be in the account. Similar to what Excel did, but Excel actually shows you the entire table from 0 to 20. You want to go straight from the knowledge that Pop has a 6% rate, he's putting in 500 bucks a year, how much is going to be out there in 20 years? And that's what the next video will help us establish, is how to get from 0 to 20 without having to go through all of this. Although this is cool, it is, we don't want to have to do it this way. So if this has made you sick to your stomach, you don't have to watch anymore. You can just use the Excel method. I'm going to go with 2 more videos. The first video is going to introduce something called a geometric series, which is actually happening here, which you might not realize. And the second will show you how to use that geometric series to get the answer to our question. So if you want to stop watching, totally fine. Otherwise, we'll see you in the next video. Okay, so here we are. Let's stop shaking. There we go. What we are going to do now is we're going to take the work we just did in the previous video, which was to establish these awesome expressions to give us values at certain years. And we're going to generalize them for any given year without having to know the year before it. Because that's the key. If you think about it, what we did in the previous video, this is good work, right? I mean, that 4th year was good. But in order to do the 4th year, we had to have the 3rd year. And the 3rd year, we had to have the 2nd year, and so forth and so on. What we really want to do is kind of analyze what was going on there and see if we can get, for example, to year 6 without having to do year 5. or to get to year 15 without 14, 13, whatever, and to get to year 20, like Pop-Pop's example, without having to actually go back and do 19 through 0. Now that's what Excel did, and if you want to use a spreadsheet, you're not watching this anyway. But if you want to see mathematically what's going on with formula, in a formula aspect, I want to show you here. So what we're going to do is, I want to do a couple things. The most interesting thing to me about this math is this part. The part where the exponents march down one after the other. Now I want you to notice something once. We're going to come back to it in about 5 or 10 minutes. You see how every one of these terms always has a 500 on it? Since we have that, by the distributive property of math, we can factor that 500 out and then multiply it back in when we're done. So just make a note of this right now. We are going to do that. I'm going to put a note to myself on the board up here. Don't forget the $500. Because I'm ADD, and I might forget if I don't write it down. So what I'm going to do is I'm going to ignore all those $500, and I'm going to rewrite this expression for year 4 here without the $500. We'll put it back in later. And I'm also going to knock down the amounts, because instead of calling this 1.06, nothing wrong with calling it 1.06, of course. There's absolutely nothing wrong with doing that. I'm going to call it R for the interest rate. Okay. You know what? No, we're not. Maybe we are. Yeah, let's do it. I'm thinking on my feet here, I apologize. And I'm thinking that we weren't going to do that, but if I call it something else, you can use it in more cases than just this one. Let's generalize. So I'm going to call this 1.06 just the variable R for interest rate applied. So if I look at that, this is really R to the 4th, forget the 500 for now, plus R cubed, plus R squared, plus R to the 0. I'm going to put that R to the 1st plus R to the 0. The reason I'm doing that, if I forget this 500, that doesn't leave 0 behind. Remember, distributive property is a multiplication, not an addition. If I factor $500 out of $500, it leaves the number 1 behind. Now, 1 might look kind of funny. You can call it 1 if you want, but I'm going to call it R to the 0, just so it keeps with our little pattern here. R to the 4th, R cubed, R squared, R to the 1st, R to 0. The previous one, up here in year 3, we can rewrite that one too. Watch this. We can rewrite that one. Take all this away. We can rewrite year 3 as just R cubed plus R squared plus R to the 1st plus R to the 0. It's much easier to look at. It's missing the $500. We'll deal with that, I promise. Over here, year 2. Year 2 is going to be R squared plus R to the 1st plus R to the 0. Year 1 is R to the 1st, R to the 0. And technically speaking, year 1 is just R to the 0. So you're seeing the march of the exponents. They're going R to the 0, then R to the 0 plus R to the 1st, R to the 0 plus R to the 1st plus R squared, and so forth and so on and so forth and so on. It's a neat progression. Now that progression keeps going. If we do it like this, the math becomes easier, but only a little tiny bit less tedious. What we want to do is we want to be able to analyze it for any given point without having the points in front. So what we really want to do is, given a future time, and we're going to call that, we'll call that T years later. What's the value? What's the value? What's the value? Okay, so what's that future value, using the language from the project? What's that future value? So rather than call it an FV for future value, which I know I use in the problem, I'm just going to call it F for future value. Okay, F. Well, using our little mathematics that we were using over here, that would mean we have to take the interest rate and apply it T times for T years. Right? For 4, the first exponent was 4. For 5, it would be 5. For 6, it would be 6. And you just keep on going and going and going. The next one would be r to 1 less than t, which would be t minus 1. This might upset your brain a little bit, and I want to make sure I don't upset anybody. On this one, the first one here with 4, it went from r to the 4th to r cubed. 3 is 1 down from 4, so 3 is 4 minus 1. T minus 1 would also be acceptable over here, and the reason we're excited about t minus 1 is that's even more general than putting a number in there. The next one would be r to the t minus 2, and so forth. And eventually, you're going to be done by r squared, r to the first, r to the 0. I mean, eventually, they're all going to, I shouldn't say that. They're at least going to have r to the 0 on them if you go all the way back to year 0. If you go to year 1, you'll have these 2. Year 2, you have these 3. Year 3, you have those 4, and so forth and so on. So you can actually see you've got an extra term than you have years. Okay, now I'm going to share with you something that one of my favorite math profs of all time showed me in my undergrad work at the University of Delaware. Dr. Peter Monk, love you. He showed me a way, because we got to this point, we're all looking at it and going, man, that's just a mess. And he said, yeah, it is a mess. Because what you really want to do is, you want to get this down so there's one number that you can plug whatever the value t is into, and out comes the value. So in other words, you want all these t's to go away and be replaced with just one t. And what blows my mind is, here's what he said. He said, take this equation and multiply the entire thing by the interest rate again. And as students, we sat back and we said, why the hell would you do that? That makes it even worse. And he said, no. Not that one. But come down here, and I'll do this in red, make it pop out. He said, take that f, that future value, and apply the interest rate one more time to it. So in other words, take the interest rate and apply it to the future value. And to make this easier, it probably isn't going to seem easier, but it will be. I'm going to put it up above here, because that value is going to be more than this value, because we're going to apply an interest rate to it again. So if you do that, hopefully you'll see what happens. This one goes from r to the t to r to the t times r, which is, if you remember your previous math, r to the t plus 1. So if the variables are screwing you up, pretend t was 4. So you'd have r to the 4th. If you multiplied it by r one more time, you'd have r to the 5th. It'd be 1 bigger. So that's r to the t plus 1. This one here would become r to the t. Because, if this was t minus 1, say, for example, 3, and you multiplied it by r again, it would become 4. And this would become r to the t minus 1. And hopefully you're noticing what's going on here. Plus, everything down here, the exponent is getting 1 bigger. So this squared down here is going to become r cubed. This first power is going to become r squared. And this 0 power is going to become r to the first. Now, if you feel like I did when I was sitting in that room, at this point I was starting to feel my breakfast start to percolate, like I wanted to vomit. And I think Dr. Monk, in his kind of pedagogical brilliance, realized how sick we were all getting. And he said, okay, I sensed the impending vomitousness. And he said, draw a line under that second equation. And he told us to subtract them from each other. So in other words, he said, everything here, subtract from everything there. And we kind of grumbled a little bit, but then we saw something kind of neat. So over here, nothing interesting happens. You simply get f times little r minus the same f. But then we saw something kind of cool, because check this out. You got an r times t plus 1. That's going to be there, because that's in the first one that gets subtracted in the second. Then you've got an r to the t that subtracts off this r to the t. In other words, these cancel each other. And those cancel each other. And you see this t minus 2 that's right here? There would be a t minus 2 up here in line that would cancel that one. And this r cubed would have an r cubed right before this r squared. And that r squared would cancel that r squared, and that r to the first would cancel that r to the first, and that r to the 0 is the only one that isn't canceled, because we got rid of it when we multiplied it by r. So I'm going to put, at this point, to make life easier for us, I'm going to put minus 1, because r to the 0 is going to be equal to 1. Remember how we talked about that back there, how we put r to the 0 to see the pattern? The pattern has now collapsed. The pattern's gone. It all canceled. And you're left with simply that 1 at the end. So just leave that 1 there. It makes life easy for us. And at this point, the room started getting more kind of voluminous, because we said, holy crap, that only has one t in it. All the other t's that were in there are now gone. There's only one t left. But then we looked over here and we said, but there's two f's. Ideally, what you want to have is you want to have the f on one side for the future value, and you want to have this expression on the other side. And then somebody in the back of the room, who was exceptionally clever, whose name rhymes with Bon Wool, said, hey, wait a minute! We can actually factor this f out over here and leave behind an r minus 1. Class is pretty impressed by that, not going to lie to you. But what's cool about that is it's a way of turning two f's into one. Legally, obviously. Legally, mathematically. And then, my classmate, I think it was Julie, I forget her last name, but Julie said, then we can divide by the r minus 1 and put it over here, and you're left with f equals r times t plus 1 minus 1 over r minus 1. Now, I want you to count something for me. How many t's do you see? I only see 1. And that's the power of this. What you just did was you derived what's known as a geometric sum from a geometric series. If you look at a geometric series stretching out to t, the tth power, you can collapse that series down in value to this in any way. We weren't actually doing finances in this class. I think it was a calculus class, actually. Infinite series and finite series and things like that. But this applies beautifully to what we're doing right now with this annuity. In the last video, we'll show you how to take that formula. Put that $500 back into it, and figure out how much the whole thing's going to be worth at the end of the day. Cool. Hang on. We'll get to it.